Thank you. Hello, everyone. My name is Domagoj. I'm here to present a small team from Croatia that works a lot on development software and ecological modeling in general, but we are also developing software for different purposes, and one of that is literature review and meta-analysis. For this task, we are tasking LLMs to do some automated inference of text data. And now I'm going to show the implementation, the theoretical implementation for soil data aggregation. In talks till now, we heard a lot of about soil health and definition of soil health, but foundational variables that are measured in literature are very numerous, and it is going to be even more prevalent with in literature with development of IoT technology, remote sensing, and so on. So it's very hard to gather all the knowledge about soil data and soil health data without the use of technology. So here is where data mining comes in mind. Data mining is a tool, is a method to approach data gathering from online sources or any other source that can be computationally read. And it can be very powerful to gather data, to summarize data about certain problems, certain tasks that we are doing research on. So with data mining, you are able to gather data to summarize specific problems through data, and through that you can create meta-analysis around researchers. So you can find a new long-term trends in data, especially from older research and newer research. When you compare those two things, then you can do also climate change assessment from literature, or even direct anthropological impact. So now, how do we access the data? How do we interpret the data from text or from literature? We have some challenges in that area that we have to solve, and that is problems with data in textual form and data in non-machine learn readable form. So in textual form, that is maybe easier to fix those challenges, or to overcome those challenges are actually the human factor problems. So we have artifacts from formatting the literature. So every publisher has different format standards, or we have problems with OCR reading. So if we transfer PDFs from older literature where the text is not textual but images, then we have some issues here. And we also have challenges in non-machine readable formats when reading graphs, charts, images, and so on. To solve these challenges, we can use LLMs. We all know what LLMs today are, right? Large language models. And the most famous one is ChatGPT, that I think maybe everyone here uses for something. And the others are Gemini and Llama. Those three are very large language models, and to train them, you really need whole data centers of computers and a lot of money. So ChatGPT is developed by OpenAI, Gemini is developed by Google, and Llama is by Meta or Facebook company. So how can we utilize technology like this to do inference on literature and do a review of literature of soil, for example, soil data? So if everyone tried to do inference with these big generalized AI models, you saw that sometimes those models tends to hallucinate, to made their own data, especially their own facts. They mix up the facts, and you have some problems with those models. However, there is a family of models that can be fine-tuned or retrained quite easily on maybe smaller machines. And those we call, they are still large language models. They're quite big with, they have like 3 billion parameters. And they are still trained or on big foundation of foundational data set, but they are smaller in terms in parameters if they are, for example, ChatGPT now has more than 1 trillion parameters, while Phi-3 by Microsoft has 3 billion, not trillion, but billion parameters. So with smaller LLMs, you can actually retrain the parts of this neural network and make it more specific for the task you are holding, you want to do. So we are currently dealing with Mistral's AI models and Phi-3 by Microsoft. Both of those models are openish, so Phi-3 is open source and Mistral is openish. I think it's Apache licensed, and you can use it to retrain it for your task and your purposes. So this is one more reason why we use those smaller models. You can see the difference in price when training the certain models. You can see the first ever transformer that was first GPT, right? The cost of training that kind of model was $900, and then you have like Gemini Ultra, that cost of training that model is more than about $200 million. So the cost of training large models is not actually acceptable for small teams, for small tasks that can be retrained on these models. So how do we approach our training? So it's actually a fine-tuning workflow that is quite common in this area. First, you need to tokenize the text. It means to transform text to some kind of machine-readable format, not just machine-readable, but neural network-readable format. Then you need to set the instruction set for the model. For our purposes, the instruction set is quite simple, because the instruction is extract data from this text. Then you have to create prompts for searching the data in the text, inference, and do the inference on the data. And of course, in the end, you need to format the inference into something that's more readable, that can be saved into comma-separated values or database or something else that can be used after for meta-analysis and on. So first, you need to know how to prompt engineer. I think that's quite simple in this case. You need to ask the system what is about your problem. On the left is some generic example for Phi-3 mini model, and on the right will be an implementation for soil. This is just an example. More complex is something like this, where you have input text that analyzes, that shows the snippet of the text that we are expecting, that we could expect in the literature, and the label or the output we want from our model. And of course, if we add the instructions, this is going to be something like this. When you have instruction for the model, then you have the input that I need to emphasize. These are only shortened examples of the inputs. The inputs actually are tokens of 2000 tokens for input snippets of the publications of papers. And the output is actual output that we want to have from the model. And of course, we had to create the data set for fine-tuning. So the data set is created by mining the large amount of literature. and creating the snippets of text. Then the text is manually labeled, so what we expect from the model to say to us. And then we do the fine-tuning using our GPUs and to make the model do only what we wanted it to do, not to hallucinate anymore, just to do inference of the text and to tell us exactly what kind of data is in this text. So our data set was consisted of about 1 million prompts. We did use some manual work to label it all, but after I think 1,000 prompts, you can actually use AI to retrain to fix the prompts again. So you can find the errors. How to say it? You can refine the data set using AI that you just trained. So it's a cyclic process. So we ended up with a data set of about 1 million prompts. That was maybe 1% manually labeled, and the other one was AI helped, so augmented data set. So the training on Phi Mini took about 7 days and 13 hours of training, and it was actually quite accurate. Still a bit hallucinating, but 93.63% is quite good for detection of data. And it was only trained on one node with 2 SLI connected RTX 8000 GPUs. It's maybe a bit high-end GPU, but still not as good as GPUs that are running ChatGPT or something like that. So yeah. So where are we now? Cost-wise, we are about between 3,000 and 100,000 euros. Actually, our training cost are about 10,000 euros. And this cost is with the cost of the equipment and the energy and time that took to train the model. So everything I talked about is just a small part of the whole mining system, data mining system. We actually developed a whole underlying framework for search, download, and transformation of literature. This toolkit is still not available online, but it's going to be, I think, tomorrow or day after tomorrow on this link. And it's part of another research. And when you are utilizing the whole framework, you can actually create a very centralized knowledge base of the task you want, especially for our purposes and our model. It was a soil health data aggregation, but in this part, it was more about, but it can be used for other purposes as well. So for ecological modeling, gathering aggregation of data as well, and so on. In conclusion, LLMs hold significant promise to revolutionize health data, especially by automizing data extraction from vast array of papers and scientific literature, which we can actually accelerate scientific discovery with this type. So especially people who do meta-analysis, they can actually get faster review. They don't have to manually check a large amount of literature. They can just use something like this model to create the review themselves. Also, LLMs offer immense potential for automating soil health data extraction. So all the data you are gathering and you need for your models, maybe you can use by using this kind of systems, right? So the only issue here is that you still need not significant, but some initial investment into computational resource, maybe cloud resources for computation to fine-tune these models. it's something cost trade-off. Are you going to give more money to make people work faster, or going to do work manually like you did before, right? So I need to acknowledge those three projects are already using system like this to gather data. One of the projects is about plastics in aquatic and terrestrial environments. Another one is about functional and ecological characterization of soils. And this project is one that we are implementing this mining system. And of course, there's a project that where we developed the mining framework as well, the EcoQuant. Thank you for your attention, and I'm ready for questions.